I wonder where that name came from. So yes, I use a baseball bat of mass m1 moving at velocity v1 to hit a ball of mass m2 moving at velocity v2. This is an elastic collision. Ignore gravity. Yeah, also ignore rotation for now. And so the first question that I need to pull up, what? How fast are the bat and ball moving after the collision? Do you guys remember how to do elastic collisions? What is the relative velocity thing? Oh, if the bat stays still, that's still kind of tricky because if you move to the reference frame where the bat is still, after the collision, the bat will start moving again. Yeah, the bat is, oh yeah, no rotation. I mean, I'm holding the bat. I'm not just gonna let it like fly. So yes, these are just 2 point objects hitting each other, colliding. So yes, what people have been saying, momentum and kinetic energy are both conserved. This is right, yeah. So I don't know if you know the formula for like it does like because here I didn't give you numbers, right? So it's kind of tedious to work through the whole like energy is the same, momentum is the same thing. Yeah, I mean I'm not gonna work through the equations, but I want to see if this looks familiar to anybody. V1 initial. Anyone see this before? No. Yeah, I think you are allowed to. I mean, you can use any equation on the exam. Like, but yeah, this is the exact formula for all elastic collisions, like in one dimension. So do you need to first derive it? I don't actually know. I think you should be allowed to use it without deriving it, but probably, yeah, like consult somebody else. I don't know. What is the numerator? This is 2m2. 2m2. So yeah, I mean, I won't go over the details of how to like derive this formula. I don't actually know if people use it much either, honestly. It's been a while. But here it is in case you want to know it. And you can also like, it's a fun exercise is to check for simple cases what this formula gives you. So let's say that, for example, you can check if M1 and M2 are the same mass and they're moving at the same velocities inwards or something like that. That will give you a nice answer. What is the right answer? Yes, these are the answers. This is the answer to the question. I just gave it to you directly. What does the second line say? I mean here? I'll just fix that. Like, I don't know how important this equation is. If you haven't learned it already, you probably don't need it. But like, I think it's cool to take, yeah, you can derive this from conservation of momentum and energy. Though it like probably takes a while. But why is this true? Yeah, I am not going to explain. I'll just skip. Why would you derive? Oh no. Oh no, what did I just do? There you go. Okay. Anyone have any more questions about this? Can we use it for A/B tests without derivation? Yeah, like again, I'm not sure. Like you'll have to consult somebody else for that. But like I'm pretty sure you can. Yeah, I'm not sure. Okay. Anybody have more questions about this part? What state of CO2 are you tasting? Can you guess and check? I don't know. Wait, I feel like probably not. Like on the AP, you probably want to like derive something explicitly. Yeah. But if you're doing a multiple choice, no one's gonna check. CO2 gas tastes weird. So now let's move on to the second question in this section. Oh, right, there's no multiple choices here. My bad. Yeah, I guess like probably we'll have to write out the derivation. But if you have like nice numbers, then you should be able to, if you start from conservation of energy and momentum, then it should be easier to derive it than the general case. Oh, no derivations on the AP this year. 10 more minutes. Okay, yeah, I don't really care. I got through everything. So yeah, let's read this question here. If the ball is a baseball, then the collision takes 0.01 seconds. If the ball is a softball, then the collision takes 0.1 seconds. Assume the bat exerts a constant force throughout the collision. Note, assume. I don't know if that's true. What is the force exerted by the bat in both situations? But I assume that this is true for the sake of this problem. Explain qualitatively why it hurts more to be hit by a baseball than a softball. So as everyone's already been saying it, but this is an impulse question. So why is this an impulse question? Someone explain. Yes, impulse equals force times time. What is impulse also? How does this help us? Yes, okay. Impulse, well, it's not MV exactly, but I think I know what you're saying. Yeah, impulse is the change in momentum. So that would just be M2 V2 final minus V2 initial, which is just V2, I think. Right, everyone knows what's going on. So yeah, F equals M2 V2F minus V2 over T. And if T is small, then F is big. And it hurts. Big forces hurt. And if T is big, F is smaller and it hurts less. J is impulse. I'm not sure, do people use J for impulse? No, yes, maybe. What? Okay, I learned J is impulse. So this is maybe something useful to know. Okay, any more questions regarding this? My teacher hates J. I guess your teacher will hate me. Okay, I'll move on to the next question. So now, okay, well, ignore that first line because it already takes 2 seconds in this formula. So, oh, okay, delta P, just use delta P. Let's do that. I think delta P is honestly probably better, but I don't know if people use J. It seems more common to me. So question C. Find the work done by the bat on the ball. Anyone have ideas for this? Right. Work energy theorem, or I don't like to think of it as a theorem, but like that's just kind of the definition of work in my opinion. So like doing work, the bat doing work on the ball means that the bat is transferring energy to the ball. Like, how is this a theorem? It's just like the definition of work. Okay, work energy fact. Or unless you define work as F times D or whatever, but that's another story. So yes, what variables are we about? Oh, I wanted to clarify that. Just to simplify things, I'm gonna allow using V2F and V1F in this. So Yeah, so as everyone has been saying, it is the change in kinetic energy, which is 1/2 m, the change in kinetic energy of the ball, 1/2 m2 v2 f squared minus v2 squared, close parenthesis. Papoon. Why is this mouse not working? I'm actually so mad. How do I get it to work? Turn off. Can the presentation be shared? Actually, yeah, that's a good idea. I'll put it on the website after. I think probably. Okay. Yeah, it has been posted above before. Well, like one specifically for this physics stuff. Yeah, it's right there. Yes. So this, yeah, this is the change, is the work. Ft over m, 1/2 m. Wait, what are you saying here? Oh, wait. No, I don't think you can say that because Ft here is the change in velocity. And this is like, you're taking, like you can't relate v2f minus v2, the square of that, to this, v2f squared minus v2 squared. Okay, yes, I am Jeremy and I like physics. Any more questions regarding this part? All right, so find the distance traveled by the bat during the collision. I think it's not too hard to do this. It should be pretty straightforward from what we've seen. I never would have guessed. Wow. Oh, well, displacement distance. Yeah, I mean, it's a like, I am assuming the batch is kind of moving like this, so it doesn't really matter. It's like moving in one direction. Can we use F? Yeah. Well, okay, I'm sure everyone knows what's going on. Let me move this. So work is force times distance. And then thus we have a formula for X. Any questions about this? Nope. Okay, now here is the, whatever this is called, the punchline. Find the average velocity of the bat during the collision. What do you notice about this average velocity compared to the bat's initial and final velocities? Why does this make sense given our assumption that the bat exerts a constant force throughout the collision? So let's write down here X. Oh my God, I can't work this thing without a mouse. Oh, can you hear me? Or maybe, can other people say? Okay, so the reason why the work done is this minus that is because like work, so energy is a scalar. So like you're not like decreasing the energy when you decelerate it to 0. Like wait, so like when you when you're decelerating it to 0, you're not like giving it any energy. You're taking energy away from it to make it 0. And then when you like speed it back up to v2f, you're adding energy back. So like, does that make sense? My mouse is not working, I'm sorry. Okay, so I can't tell if like people have like given me the answer that I was wondering. Like I can't, because I can't work this without a mouse. Okay, Let me try and, it's fine. So can you guys say again, did you notice the thing about the velocity? Stop giving me time updates, I know. Okay. So what did you guys notice about the average velocity? Did you figure out what's going on? Okay. This is meant to be interesting, okay, fine. Gotta take it like that. But yeah, so how did you find that average velocity? Wait, what? Huh? Okay, wait, maybe this isn't what I wanted. Okay, let me explain. So average velocity is total displacement over total time, right? Yes. So if we take our expression for x, divide it by t, I think it's kind of hard to write here. So no, that's not what I wanted you to do. See, this is what I meant. So v2f squared minus v2 squared divided. So this is x, right? And then fm2 v2f minus v2 over t, right? This is x, and then you divide this whole thing by t. So this cancels, this cancels, this becomes v2f plus v2. And so the final answer is half v2 f plus v2, which is, yes. So the average velocity is indeed the average of the initial and final velocities. Like the average velocity we calculate for x over t. Yes, and that is because the bat exerts a constant force. And so the acceleration of the bat is constant. Okay, okay, let's move on to the next question. Anyone have questions? By the way, it's 5, so, or it's 5 for me, 6 for you, possibly. So it is okay if you have to go somewhere. I'm not judging anybody. But I am going to continue if that is what people want. Or if you don't want me to continue, then just leave. So okay, so anyone have questions about E? My rotational motion problem is 3, unfortunately, but we're almost there. Bad. Okay, so I assume that everybody is okay with question E. If you have any questions, feel free to ask them whenever. So now let's read question F. After being struck, the ball follows a parabolic trajectory. That is, until it collides totally inelastically with a poor bird hovering in the air. The collision happens at the top of the ball's trajectory, and the bird has the same mass as the ball. Luckily, after the collision, the bird is able to fly away. So the bird did not die, okay? I made sure that this was going to happen. Suppose that if the ball hadn't hit the bird, then it would have gone a distance of x from the location where it was initially struck. So at what distance does the ball actually land? Here's my beautiful diagram. I've used that word already, I can't do that. My spectacular diagram. So I give you x, which is how far it would have gone if it made the whole trajectory, but it actually hit the bird, so it falls down here at a distance less than x. So what is this distance? Yes. The time taken, so okay, that's the important observation. So horizontal and vertical velocities are distinct. So that means that the time taken for the whole thing is the same, whether it hits the bird or not. Okay, so yeah, so we only care about the horizontal velocity after the collision, right? So like the horizontal velocity before the collision is like some number Vx. And then after the collision, because it's inelastic, Now the mass it's hit the bird, which was originally stationary. So that means that the new velocity is Vx over 2. Yeah, the collision is perfectly inelastic. That's what I meant to say. It says totally inelastic. So yeah, so the velocity is halved, and because the time taken to fall is the same, it'll travel only half the distance it was supposed to. So the distance traveled will be 3x over 4. What? Okay. Any questions? Questions, questions, questions. Yes, the bird is floating in the air, moving at 0 velocity. It is hovering. So that is why the collision happened like this. Okay. So last part of question 2. The ball bounces elastically on the ground, and an impulse of static friction causes it to begin rotating. Has any mechanical energy been lost? Explain. Yeah, I know birds can't hover. Yeah, so guys, put yes or no for this. What do you think? Okay, so we've received a variety of answers. Yeah, it's perfectly elastic. So that means that the actual collision, in the actual collision, they don't stick together at all. But like there is static friction. So like none of the energy is lost by the fact that they collided. Okay. So some of you have gotten on the right track. So what I meant to explain by this is the fact that static friction never takes away any of the mechanical energy of a system, because the way static friction works is that let's say something is rolling without slipping, right? And there's static friction this way. So the energy that is lost from the system by friction is the work done by the friction force, which is work equals F times X, which is the displacement. But by the definition of static friction, the point of contact is not moving. So that means X is 0. I'm sure, have some of you heard this before? Yeah. Yeah, the bottom of a wheel doesn't move. And also the bottom of anything that has static friction acting on it does not move, because by the definition of static friction, they can't move relative to each other. Otherwise, it would be kinetic friction, and in that case, they would lose energy to heat or other things. Yes. Okay. All right. Any questions? All right. Is the velocity of the ball reduced? Oh, okay. Yes, I was actually going to explain that and I forgot. So the thing is, of course, the ball has started rotating, right? Where did the energy come from? So it must have come from the linear translational kinetic energy. So the ball has to have slowed down a little bit. Yeah, exactly. So the thing is, static friction does not take away mechanical energy. It transfers mechanical energy between rotation and translation, I think. This might not be always true. Yeah, this should always be true. It always transfers mechanical energy into a different form. So yeah, if you actually like find the sum of the rotational and translational kinetic energy, you'll find that it's the same as the original. Yes. Okay. Anyone have any questions before I move on to the next? This is